Hello, in this video we're going to be talking about Math 3, Unit 4, Assignment 1.4 through 1.3. And although much of this section is very familiar to a traditional Algebra 2 class, there are some sticking points that are hard to explain to students and hard to even understand occasionally what the book is thinking with their answers. So the crucial facts to eliminate a lot of the confusions, if you come back to these ideas, especially number one, is that even roots do not yield negative values. An even root, a square root, a fourth root, a sixth root will never give you a negative result. And a lot of the times what we have done is shortcutted our way past something, so it looks to the students like sometimes you put a plus and minus, but sometimes you only put a plus. And so the truth is that even roots never yield negative values. And so if you keep that focus, you'll understand why things happen, where sometimes when we are simplifying, even radicals that contain variables will get a situation where there's absolute values in the answer, because an even root can never have a negative answer. And when we're solving, sometimes we'll get an answer, the absolute value in the expression will create two solutions, positive and negative. So it's not that the square root is giving you positive and negative. It's actually the fact that you had to have gotten a positive answer. You put an absolute value that gives you the positive and negative. I think that might not be super clear, so I want to work a few problems to explain better what I'm talking about. And students might, again, argue with you about answers because a calculator only gives you a positive answer. The calculators are programmed to only give the principal root, not all possible roots. So we're going to start by looking at number 12, one of the first problems you have that you could choose. And the directions here are the problem. Find all real square roots of each number. If they had said the square root of 12 equals, we would say, I'm sorry, not this problem 12, back it up. If I said the square root of 25 equals, I would say that that was 5, because an even root can only yield a positive answer. But here, it's actually, there is an unknown value. There is some value x, and when we square it, it comes out to equal 25. And so what we want to know is what that value x is, what that square root of 25 is. And as we go to solve this, if we root both sides, we're putting a square root, an even root on. This even root can only yield a positive value. This even root can only yield a positive value, and you'll find this as a definition in the book. And so if I just say the square root of x squared is x, x might be positive, x might be negative. We don't really know. And so if we put absolute values around that, that guarantees this variable is that what we got out of under a square root is positive, whether the variable is representing a positive or a negative number. And then solving an absolute value means that there's two possible cases. It could be that x is actually positive 5, or it could be that x is negative 5. Now, you probably haven't explained it in that lengthy a way to your students, and you may or may not choose to do that this time either. But students, the confusion of sometimes having plus or minus 5 and sometimes having only the positive answer, or making such a big deal about absolute values when just a minute ago you said plus or minus was the answer, is explained because this is really what's going on when we do square roots. So a lot of us, myself included, have taught for years that when you add the square root, that's when the plus or minus comes in. And that's because when you add the square root, you're looking for an answer to something that is a variable, that is an unknown situation, and you're having to put absolute values. We just don't usually show those steps. It's fine with me if you, however you choose to teach that, but the point being, there is more consistency in it than what it feels like to the students. The even root will always only have a positive answer. And it's because we're bending over backwards to make this positive that we get two answers, a positive and a negative. This problem, I thought, oh my goodness, they didn't put the right answer. So this is just a careful reading problem. If I get to the spot where I am at the square root of x squared equals the square root of negative 64, it's asking me for all real square roots. real being the key word here, this will be an imaginary square root. So you might want to have your students think together about what that will be. Eventually you should get plus or minus 8i. Since they just barely learned imaginary numbers, and it's a good chance to talk about that. But then the answer would be no real roots, no real square roots. And so that would be our answer on that one. So just because they just barely learned I, it's a good chance to take an opportunity to talk about that again. And on number 15, when we simplify this, now the square root is already on there. There's not a guessing about, there's not another side that's x squared, some magical number that when we square it, it equals 9b squared. They already have that square root. This is called the principal root. And so we will only need to give the positive answer. An even root is going to only yield a positive answer. If you take this and however you explain this, whether you do a factor tree or list factors or however you choose to explain this, if you get to 3b, then you need to make sure that you have just put a positive answer. Since we know 3 is positive, it doesn't need absolute values, but we don't know if b is positive or not, so b would need absolute values around it. So as you look at the answers, you'll see absolute values. We avoided that cleverly in Algebra 2 because we often made a statement, assume all variables represent positive values. Then we didn't have to think these thoughts. We would like our students to have to think a little bit about that. I need to make sure it's positive. Some people wanted to know if a student put absolute value of 3b, should I accept that? That's something your PLT should discuss and decide, like how lenient are you going to be on their use of absolute value. There's sometimes where it's clearly wrong, so you wouldn't want to take that. But I hesitate to be overly lenient because you might have students just put absolute values on every single answer on a test, and just because they're wanting to avoid thinking it through. So we should, and they will get some wrong because some of them don't deserve absolute values. So we should have them go through the process of thinking through when absolute values are needed and when they are not. For instance, on number 16, I have a to the 8th, b to the 18th. And on that, after breaking down however you choose to pair things up or take this route, you'll have 4 pairs of a's coming out and 9 pairs of b's coming out. Now, a, I do not know whether it's positive or negative, but a to the 4th, I am sure is a positive number because anything to an even power is positive. B to the 9th, I'm not sure whether that's positive or negative. So what you'll see the book doing is not putting absolute values around all the variables, only around the variable that really needs it, the one that might be yielding a negative. We know that coming out from an even root, we should be having a positive answer, so we're making sure of that. And then this one is an odd root, and so we don't need to worry about it. The rule is even roots yield positive answers. And so this could have a negative answer, and so negative 5a will be fine for that. We won't need to worry about absolute values or making a negative or positive or all the other crazy things students might think. So as you're going through this assignment, I would say this piece is really confusing, and maybe a little bit the plus or minus up here is a little confusing. I don't think the plus or minus issue comes up too much, but I do know the absolute values continue to haunt you through the chapter. Well, they do have to be able to put a plus or minus in when they solve these equations. And so that is true. And I put this here, solving the absolute value expression then creates 2 solutions. And that's what happens over here on a problem like this. X squared equals 0.25. Then when I square root both sides, I'm going to get the square root of x squared is the absolute value of x. And the square root of 0.25 is positive 0.5. And from this, I'll get my 2 possible solutions. Okay. I went through and did every single problem in this book. I thought you might not have time for that, so I wanted to give you my insights. I personally didn't like 34. 34 seemed to be need excessively careful reading. You might like it. If you like it, feel free to assign it. But if it was me, I would probably leave that off. That was just a little too painful. But I loved 35 through 42. These seemed like just beautiful class partner discussion problems. Maybe the next day as a warm-up, you and your partner look through 35 through 42 and decide on your answers. Then we can call on people. We can talk about it. Helps us deal with some of the positive, negative issues that are so tricky. 43 and 45 are really nice partner discussion questions for open of class or transition time between two things. Some of them are really, really thoughtful problems. Sometimes these don't make the best home problems, although if you have a really high-end class, I think they would. It'd be nice to send them home and re-talk about them. But they do make really good discussion questions. And so, for instance, on number 43, how many square roots of integers are in the interval between 24 and 25? This just lets them think a little bit about integers. Now, if there was some number that was square rooted and it came out to 24, and another number that was square rooted and it came out to 25, we can actually square those to figure that out. I think this is 576. And then we would be trying to think of how many numbers in between would we be square rooting. So how many square roots would fall between 24 and 25? So what I did was I just subtracted those two. Is 526 or 576 right? Yes. And I got that 48 numbers are in between there. So 577, if I square root that, I'm going to get something like 24.1 or something like that. 580, all of those numbers, 600 will give me something between there. All 48 numbers between 576 and 625 will give square roots between those. So it's an interesting thing. Is it a test question? No. Is it a nice discussion? Yes. Might be a fun thing. And then 45 is also an interesting problem. It can be done with special right triangles. It can be done with Pythagorean theorem. It's easier with Pythagorean theorem because they don't have to convert back and forth in the roots. So the altitude, which is greater, the altitude of an equilateral triangle with side 8 or the diagonal of a square with side 5? And so the equilateral triangle, let's put it over here, with side 8, I wanted this altitude, then I would know that that got cut into 4. And for my 30, 60, 90 kind of people, they might have said, oh, right away, this altitude equals 4 root 3 from memorization. The student who didn't remember might have said, here's my altitude, a squared plus 4 squared equals 8 squared, and would have finally got down to, let's see, I have 64 minus 16, 48. A was a square root of 48. I would put plus or minus and all that stuff if you want the in-between steps, but since it's a positive distance, I'm going to go with the positive. And so if we break that down, we see we'll get this, but if we stop there, it's actually a little faster, which is why the Pythagorean theorem person. The square of side 5, if I want to know how long the diagonal is, again, my Pythagorean theorem person is just telling me, hey, that's 5 root 2. And so then they're left with the question, is 5 root 2 bigger or is 4 root 3 bigger? And they'll need to convert back, change this 4 root 3 into a 48, or get a calculator and use a decimal. If I was doing this in class, I might say no calculators allowed, just to force them to go back and forth between. And then they would have to convert this back. If they do Pythagorean theorem again, so that they have 5 squared plus 5 squared equals c squared, 25 and 25 is 50, and square rooting and knowing that it's going to be positive, I'd get square root of 50, and I can see, because they're in that easy to compare form, that this one is larger. When they're like this, it's harder to tell, and they'll want to convert back to this form to be able to compare them. So it's a nice problem. I might have the kids guess, which one do you think is going to be bigger for a little bit. They might just pick the one with 8s in it, thinking that that's going to be bigger, take a vote. Then I might have them do a little math with their partner. Then I might have them decide whether they want to revise their guess and give their answer and try to give a reason. So that's 4.1. Let's turn to the next section. In 4.2, let me get up here. In 4.2, we start having more absolute value woes, especially in the way the book uses them. Up here again, I have a summary of the things that I found when I looked through the assignment. If you want to take screenshots of this spot in the video, that way you don't have to go back and find that or try to copy it down really quick. that would be fine. So what I thought was 1 through 11 looked like, I'm sorry, I'm thinking about 4.3. So what I thought was number 14, I did not like the way the book says no real solutions. Although it's true, they didn't ask for real solutions on this one. They just said multiply, if possible, and then simplify. And it is possible for us to multiply. If they want only real solutions, they should put that in the directions. Again, our students have just learned imaginary numbers, so it's not bad to take the opportunity here. I would like my students to know that they shouldn't multiply and then break down if there's a negative underneath. They should put this into imaginary form, and so go ahead and get it as 2i, and then my answer will be 2i root 3. So choose whether or not you want to touch on that. It's not going to be on the test. It is another chance for us to practice imaginary in a year where they don't have very much imaginary background. So some of you might just avoid that problem, but if you want to take that opportunity, there's, I think, 3 times when you get to talk about potential imaginary things in this assignment. Number 14 is 1. Number 18 is 1. For what values of x is the square root of negative 4x cubed real? Justify your reasoning. This is a really nice discussion question. And then also number 40 gives you an opportunity to talk about imaginary numbers. And they have a square root of negative 2 times the square root of negative 3, and they've multiplied it, and they got it wrong, and what's wrong with that? So there's 3 chances to bring that up. You might kind of save those and just have those as a separate little thing. Let's work on these 3 with your group and talk about imaginary. Remember what we know about imaginary numbers. Okay, so that's those. So 18 is a wonderful conversation because most of them will think, well, this isn't real because there's a negative 4. But if x was negative, we can make that positive. So it's a really nice conversation. Number 24 also has a great opportunity for conversation like that because they have them do the problem a couple different ways. First, they have them rationalize multiplying by square root of 75 on the top and bottom. Second, they have them rationalize by multiplying by only square root of 3 on the top and the bottom. And then they can talk about which one was more efficient. And then they don't have to do this one, but they can explain how they could simplify this, what would be an efficient way. And so they can just think about what would they like to multiply by on the top and bottom and why. So it's a very nice conversation question. Let me just roll down here. Again, we're going to have the absolute value problem, and we get into this assumption that the book has. And so the book, remember, our critical fact is that even roots do not yield negative values. And so this is an even root. What we bring out has to be a positive answer. Now, there's an assumption that the book has that it does not explicitly state. That's not good. They should explicitly state this. On our old Algebra 2 book, they would explicitly state, assume all variables are positive. In this book, they assume all given variable expressions represent real numbers. So this does not have a negative under it right now. Because if it did, this would not be a real expression. So if I know that this does not represent a non-real expression, then I know, I can't really tell about y. Y could still be a negative number because to the 6th would be taken care of, but I know that x is not a real number. Is not a negative number because to the 3rd would still be negative, and that would be impossible to do this problem. And so they assume all given variable expressions represent real numbers. Based on that, they determine the sign of any variable they can. In this case, we know that x is positive. If it wasn't, that expression wouldn't be real. And then after they simplify, then we're going to add absolute values where we need to. So in this case, I'm looking for 4 of a kind. After a lot of breaking down and whatnot, I can know there's 6 2s in there. So 4 could come out. That would be 1, 2 coming out. You know what? I'm going to explain it the way that I usually do it instead of trying to shortcut. I would break this down, and I would say this was 8 times 8. And that would mean there are 3 2s and 3 2s. I know a lot of you do this simpler, much less paper using ways, but because we have new teachers teaching this, I want to show one way of explaining this. With this, I have 4 of a kind right here. Nod to Mike Lamb breaking people out of jail, but for me, I would say this 4 of a kind covers that 4th power, and a 2 can come out. There's 2 2s left inside. There's 3 X's. They don't have 4 of a kind. There's no way they're getting out. There's 6 Y's, and so 1 could come out. What I would be left with underneath would 2 2s. That's a 4. X times X times X. And 2 Y's. Now what I need to do is make sure that what I just wrote is positive. And this will be positive if this Y value is positive. So I need to absolute value that Y. I knew X was positive. If I'd brought an X out instead of a Y, I would not have needed the absolute values. Because I brought a Y out, I needed the absolute values. Okay. All right, so as you look at these, I first thought their answers to 7, 8, and 9 were wrong. They were leaving off absolute values, but now I realize that they were reasoning some variables had to be positive to begin with. So as I look at this expression, if these are real expressions, just as they are, then X must have been a positive number, just as it's written right now. Not after it's reduced. As it's written right now, X would have to be a positive number to make that a real expression. Lots of different ways you could do this, about 100 different ways you can do this, but one way you can do it is think of it all as one root and do a little reducing before you go any further. When you do that, the 3's will reduce, the X will reduce, and I will have 16X squared over Y squared. Then when I square root each thing, I will have 4X over Y. And I thought there should be absolute values around the X and Y, but when you look at the book, they only have absolute values around the Y. And the reason is they already knew that X was a positive number. This would not have been a real expression if X was not a positive number. So that's what's going on with the book. I don't think that logic should kill them. I also don't think we'll be trying to trap them with that on the test. And so, you know, I wouldn't like freak out about that. Just make sure they know to put an absolute value, for instance, on this because it came out. Let's look at this next one. I can do a little bit reducing. Let's see, before I even start, I know that both A and B must be positive because I know that B must be positive because that would make the bottom. If B is positive, then I know that A must be positive. So they're both positive. That being said, then we can go ahead and reduce, and it looks like we shouldn't need any absolute values. So when I reduce these, I will end up with 4 over 9ab squared. Then I would square root what I could. And again, you could rationalize first, but I'm going to square root what I could. I will have 9. That's supposed to be, I'll have 2. The square root of 9 is 3b, and I'd have a square root of a. And then I need to rationalize by multiplying by the square root of a. So then I would have 2 root a over 3ab. And again, I thought that the book was missing its absolute values around a and b, but it turns out by logic you can determine that both a and b were positive to begin with. And so we didn't need them. Okay, let's just practice that logic for number 9, and then we'll go on. So on this one, as I look at this, I know that X must be a positive number because these 3 things multiplied together are positive. So X must be positive. And since X is a positive, I know that Y must be positive. And so given those pieces of information, then I can go ahead and simplify this. And what I did first was thought of them all under one root, so I could do a little reducing. And so that got me square root of 3 over 5y. And then I just wanted to rationalize that. Oh, sorry, square root of 5y multiplied by square root of 5y on the top and bottom. And I got square root of 15y over 5y. This answer has no absolute values in the book, and that's because by logic we could determine that y would be positive. So that was really tricky to me. I was about ready to call Pearson and complain that they were leaving absolute values off some of the times and not other times, but it all comes thinking about, can we tell anything's positive if we know that the situation is a real number? And they did not state this at the top. So it's something, if we want our kids to understand the answers that the back of the book is giving, that's something we want to be sure and tell them. You need to assume all given variable expressions represent real numbers. Not positive numbers, but real numbers. And then this one, they shouldn't be worrying about absolute values because these are cube roots, and so there's no need to worry about things being positive and negatives. Even roots yield positive answers. Odd roots can be positive or negative, no need for absolute values. So that's what's going on in 4.2. And the last section that I just wanted to look at real quickly is, I talked about a couple of, I think we did talk about it. I know I chose to skip 47. It is a challenging problem to look at if you don't really know rational exponents. And although they learned a little bit about them in Math 2, we'll be going over those in 4.4 or 6.4. Sorry, 4.4. It's chapter 6, but our section 4. So I would skip that for now. And the last one we wanted to look at was 4.3. In 4.3, there's not any other new tricky tricks hanging around, but there's lots of times to use them. So 1 through 11 looked like what I would cover in class. Number 3 out of that 1 through 11 was a geometry problem. It was very fun to me, but it might be a distraction to your students because the rest of the assignment doesn't really need that. So it just kind of depends on whether you are feeling you have time to do that. You might take a couple of the geometry problems and do them later as practice applications. So you may or may not want to talk about that one. This has them breaking down and adding. It also gives them an opportunity to multiply binomials. They need more practice at that. They did do that in Math 2. They did do that a little bit in our Unit 3, but they could always use more time, especially when you start throwing in things like square roots, and knowing, of course, that when you square a binomial, that doesn't just mean you distribute the square, quote unquote, distribute the square to both pieces, that you need to use distributive property and multiply that out. As you keep looking, more opportunities for multiplying binomials with square roots. They learn about multiplying by the conjugate and rationalizing the denominator. These two both take reducing after they're rationalized, so that's really nice. Nice practice for those. And I would say going through 11 in class seemed like a good spot, and this would be a good place to start homework. It has some that are not too terribly hard right there, so it's a good first few on the homework. As you keep looking, number 21 is also a geometry application, and if you choose to do it, that's fine. But what I don't like about it is the direction. It says find the total area of the design to the nearest tenth of a square inch. I would have my students represent it both in simplest radical form and in decimal form. It does make sense to want a decimal form answer for a physical object like a floor and tiling, but the whole point here is to be practicing our radicals, and so just to have them change right away to decimals, I would not agree with that. 32 and 33 seem a little bit meaner than necessary for the average student. You might, if you want to give those because you just really like those, I would advise doing that in a supported situation in class with a partner or a group. Not at home by themselves. That's just an extra frustration for They could really use practice with these, so although they're incredibly boring, notice it's different stuff. There's breaking down and adding roots. There's some that are multiplying. There's some that are expanding a squared binomial. So lots of different things you can do. Over here, this section is a lot of rationalizing the denominator when there's roots. I also think 44 is kind of unnecessarily evil with the decimals. I probably wouldn't do that. It's fine if you want to, but it's not really, I don't know what you gain from that. 49 and 50, those are very challenging problems. In our textbook, they've already done rational functions, that fraction function work that we haven't done yet. That will be our next chapter, chapter 5 or unit 5. And so our students don't have the proficiency, the smoothness with fractions that maybe they expect at this point in the book. I still don't think this is a bad problem, but I wouldn't send them to do it by themselves. I might want to do that with a group. Can they figure it out? Because it does allow them to think about getting common denominators and things like that, which would be good pre-Unit 5 work to get them ready to be able to handle the rational functions. Number 35 through 38 and 51 and 52 are great class discussion questions. I personally can imagine having some kind of an activity where you had a different one of these questions at every group of 4 and had students rotate through and talk about these questions, because they're very nice, thoughtful questions, good conversations. If you put a timer up for 5 minutes and had them spend 5 minutes of the group and then move, I think 35 is not really a 5-minute kind of question. You might want to put 2 on that table so they'd have an equal amount of time. And you could steal some from a previous, the last previous sections, maybe do that at the end of a block. And that would be some time to discuss some really interesting things, come back together and ask them which questions they couldn't agree on and be able to talk about those. Because those are really nice in-class discussion questions. Not sure if they're great at home, suffering about yourself kind of questions. A higher class, if you have a higher end class, then those would be wonderful questions to send some of them home and come back and discuss about them when they get back into class. Okay, so that's the beginning of Unit 4. I'm going to stop right now for the video, but in the second half, we'll be looking at solving and graphing and how the graphs of rational functions help us understand better the solutions that we get when we solve those. So I wish you the best of luck on these. Have fun.